Hello and welcome back to the channel. It is Mark from PowerSonic and Apprentice 121. You can see we've got another array behind me here. These are 12 Trina 440 watt panels, and this is on a steel sheet roof. So it's a different mounting system to anything we've ever showed on the channel before. We're going to dive into it, see how it fixes down, how you secure these onto the structure below and get the panels performing. We're going to have or there are already 12 Tigo optimizers under here with the rapid shutdown as well, monitoring the system as always. So we've got that safety function built in there. And right at the start of the video, if you are a consumer and you're looking for solar PV and battery storage, there's a link to our website where you can go and have a look around there with our contact details as well. It'd be an absolute pleasure to propose a system for you. Safety and quality are two of the primary concerns here, and we get into all of that through the course of this install. I'm going to spin you around and take you through exactly what we've got, and we'll have a little chat through the course of the video. So we have our equipment mounted. We've just got to get the solar array up, the tap up there. Coming back to here, I'll take you through it so you can see what we've got. I'll pop a picture up somewhere up here of what we had to start with. There was a little consume unit there, which we've removed, made use of existing wiring coming down to this detached building to cover off our solar generation and also allow power for the existing lights and sockets. Minimal consumption down here. There really is next to nothing. It is just the customer coming in, popping the lights on, to have a little look for stuff, and power for charging up battery drills. So we've got the Proteus board, and we've gone for, is this an 8-way, I think? 2, 4, 6, yeah, 8-way. And we've got the SPD, which goes on the bus bar, so there's no fly lead into the line, no overcurrent protection needed for this. So we're all good on that front. On the circuit layouts, we've got the lighting circuit down here. We've got a 32 amp for the socket circuits. It's just a ring vinyl that's run around. It's never going to see anything like that, but pop that in anyway. We've got a 16 amp break here, which is for a radial to an outdoor socket. We've got our supply for the inverter, and we've then got a couple of spare ways, and there is a little 20 amp supply here which I'm going to use to drop a local socket in for our power over Ethernet to get some internet connectivity down here. We can't run a data cable down. Digging up the garden is an absolute no-go, and the route back to the router is ridiculous. So we're going to try power over Ethernet, see if we can get some reasonable Wi-Fi down here as well. But we will hardwire out of the power line adapters rather than a local Wi-Fi network. It is what it is with things like this. Ultimately, the equipment that's monitoring most of everything what is going on is in the GivEnergy system. It really is just some connectivity for the tap here, so the customer, if they want, can dial in and see what the panels are doing on a panel by panel level, and also for the Solex inverter, because you can see we've got the little dongle here. We're going to pop an Ethernet cable in the bottom there. You know, it's not the be all and end all, but hopefully we get a reliable connection down here. It is what it is. The strings are going to drop down the centre here. So this is all homemade by the customer. They've done an absolutely cracking job on this roof structure. It's rock solid. I've seen professionals do a far worse job, so full credit to them. We've got our circuit coming off into our AC isolator, and I don't know if the video that's going to be out before this or not, but there's another install we've shared this on as well, where we've adjusted the way we wire these now. So I'm coming out of the AC isolator, and this is a 63 amp variety, loads of room in the bottom there, and these are all ferruled up, so they're very well connected. We've got the feed coming out into our inverter, and also a feed coming across and down into the tap. And we pop this into some DIN rail Wagos in 6mm, so we brought the 6mm all the way down to the enclosure, and then we just tapped off that in some smaller conductors, 1.5mm, into this little power supply, just because the terminals aren't big enough to take the 6mm, and that takes the neutral and the line into the bottom, and then we're popping out our positive and negative into the CCA Connect, which is a little router which allows the Tigo rapid shutdown system to work, and also connects everything back to the internet. Pointing out with these, you'll see at the bottom we've got line and neutral, line on the right, but at the top here we've got the positive on the left, so they do swing over. We had one of these delivered last week that had been blown up. We noticed in the box it was missing its clip to go on the DIN rail, so that rang alarm bells, and yeah, it bent out the PCB board, so I suspect somebody's wired that up wrong in the past and it's come back for an exchange. Our strings are going to come into this isolator here, so we're going to bring them down into the trunk in there, run across, up into the isolator, and then they drop back down into these Waygos, you can see we've got a little linking bars in there. I've used blue and grey just because they don't make a red and white, so it is what it is there. Grey is positive, blue is negative. It made logic in my mind. And we bring in the strings in on this left-hand side here for the negative, and that goes out to the inverter. And then we're bringing the positive in from the isolator on this right-hand side here, and that goes off to the inverter. So they're running straight through the Wago. The little bridges are just for the SPD feeds. And you can see I still need to put my earth in on the SPD. We have got the earth feed into the earth bar, so that'll just loop in there. And then we've got our DC SPDs covered off. I know this is a mixture of AC and DC in the same enclosure, but all the cables are rated to the required voltage. And we do have separation. I'm going to put some blanks in here, so they're not together and they're coming through separate holes in the top. So I've made every effort, and it's just to try and neaten the install up. I think that's perfectly fine. And we've got the SPD. I know that these inverters have the SPD protection built in anyway on the strings, so it's not essential to have that. However, with this ministerial structure that we're going to bond, it made sense just to have it there as a just in case. For the cost of them, you know, it's a no-brainer to fit it, so we're popping it in. We've got our existing cables coming in for the supply to the consumer unit and the inverter. So we're all covered off there, and I won't show you around the rest of this building, but you know, the customer's got all their stuff in. But it's a reasonable sized detached workshop, and I think this will make a good space for our equipment. I'm just going to pop some of the lids on. I need to get a cat cable in here and do my earth fly lead, so I'll do that. Get the AC isolator covered on, get the trunking lid on. Actually I won't, because we still need to drop our strings in, so I'll leave that off for now. And I'll move the install along and show you a bit else of what we've been up to in just a minute. So we've got 4 panels on, nice and square. Good distance off the bottom, about 300, just over 300 at the top. And these are Trina 440s. And these are 52 volts on the open circuit voltage. So I've had to bring it in 2 strings. I was working on the maths of Jinkos, but fortunately we realised before we got too far, Jinkos are down at 40 volts. So these will peak a bit too high. So we're going to have 2 strings of 6. You can see we've got our little mini rails, and they are self-tap onto the trapezoidal roof. Absolutely rock solid, they're going nowhere. Why they're sealed, there's a little rubber gasket on the underside of these Valk rails. You can see here, so that sits on the roof and gives it a seal. And then this will all be bonded back, and a nice 12 panel array very, very shortly. Got all the panels up here. We're just going to chuck the rest down and get our 2 strings started. So we've got our strings out. There was a little hump in the flashing along the top of this roof, so we've just popped them through there. I think we would have got it through any of these, but that'll give a bit more space. So it's just dropped over, a bit of Copex for extra protection, and Nathan's just inside clipping those up down the timbers to the inverter location. So we've got our MC4s secured to the rail. We're just going to neaten these cables up, make sure they're all happy. We've got our tap, which links off back to the CCA inside. That's a data link cable to it. That's going to live on the underside of a panel, and that communicates with all the optimizers. So we take the little QR codes off these, make a little map that we've got on some cardboard over there. That gets loaded into the software when we know what panel's doing what. When we look at it in the software, it'll tell you at a panel level, and it also does the rapid shutdown. So we're just going to get these last 6 on. So we've got our first string of 6 over that way, another string of 6 over this way. All the bonding on and clamped down to the rails, and we should be good to go on that one. I'll show you it when we've got it finished. So I thought we'd have a little look at doing an MC4 connector. I'm under the Solex inverter, you can see it's DC isolator there, and I'm just popping this second string in. First thing to do is make sure you get a nice neat cut on the end, as we've got there. And then the basic principle of MC4s is to make sure you're using an appropriate crimping tool and that you use matching ends. These ones from Solex, they come with the crimps and the MC4 plugs in the end. I think they're Delican. There's a brand name on them. So you need to make sure you use the appropriate ones, because they will match up with the ones in the inverter. Out on the array, we use the LK varieties for our string input and output. And as long as you make sure those connections are mating over, you can't ever really go wrong. I think Solar Edge have a chart of compatibility, and LK have produced one as well actually, where they've tested the interconnectivity of MC4s, and they've got some that are quite happy being plugged together. So it's worth checking that. It's not, although it says in the regulations not to do it, there has been some tests done by manufacturers that will allow it. so it's worth checking. And then we're just stripping our end. Again, I prefer to use croppers if you're skilled in the art of stripping. It's not that much of a difficult job, but then you're just checking you've not damaged any of the strands. It all looks in good order, as this one does. And we're just going to give it a little trim to the right length, so we've got a nice straight cut on the end. And then we use the appropriate crimp tool. Dogs are outside helping Matthew and Nathan. So I showed them on my stories earlier this morning, absolute legends, those guys. But then we're going to go in, this is where I need my glasses, make sure we get all the strands in, then crimp, nice solid crimp on the end, appropriate tool for that job, and then we're looking at our strands to make sure they're in correctly. See in there, see that's a nice neat connection, we're tight up to the insulation, all the strands are locked in, and that is not coming out. Don't be using things like pliers, don't be trying to make your yellow, red, blue crimp set work. It's not the right way. And then with these, sorry, the big ends on these, I always get mixed up with that, go into the, what I would call a male plug. The smaller ends go in the female, so the bigger plug has the smaller pin. That's the way I always remember it. Anyway, then you push it in till you get the click, as we've got there. And you then need, if I can find it, your tightening tool. And you just give it a lock up. Now some of these will go till they start clicking, and that's when they're appropriately tight on the back. This is giving it its weather seal, so it's really important to get that in place. And other ones use a torque tool, so make sure whichever connector you're using, you either torque it down or wait for the click, depending on which option you've got. And that's kind of the finished product. So we're good to go. That can plug into the inverter. The inverter on this end, so that's the positive input, requires that plug. But it's always worth checking. I get mixed up with these. They swap around from the panels to the inverters based on what end you're putting on. So double and triple check what you're doing. And that's it for the MC4s. I've got a half-an-hour video on this on my YouTube channel from about a year ago, which is way, way too long. It's a much easier topic to explain than I gave it credit for through the course of that. But if you want to see an expanded video, there's one of those out there as well that you can go off and watch, should you wish. So just to show you the roof here, these are the 440 Trina panels this time. We swapped away from Jinkos, and these are performing very nicely. The sun tracks across this south, it's all open, so we're late in the afternoon now and sun's over that side, but it's been doing very well. We've had between 5 and 6 kilowatts of generation out of it. Now obviously the peak here, you're looking at 440, you're looking at about 5 kilowatts ish, a little bit more than that, so they're about on par for what we would expect this time of year. We're into September now. This roof's been designed and built to a pitch that best serves generation through the course of the year for this consumer. You can see we've got our spacings off the bottom. There's still the gutters to be added, and these are going to be built out, so we're a nice distance away there. It's 300 mil off the bottom. I think we're 325 off the top. We've got a good 300 off the edge here. I think it's actually more, it's more like 400, and it's the same at the other side because we plonked it slap bang in the middle of the roof. You see I've just interrupted Nathan with his bird guard. So we've got the bird guard up there, bird guard across the top. He's just popping the bird guard in along the bottom. These are always a little bit tricky with the steel sheets because they do have the grooves up and down, but we're just trying to stop pigeons more than anything. They're the ones who are going to go in there and cause the most damage, so he'll get that popped away so it's nice and secure. You can see we're dead flat, dead straight. The customer did a cracking job building this roof. It is absolutely duck pond level, so there's not a ripple in it anywhere, and it's gone down super nice. We're really happy with the result. I'll show you from the garden. You can see there's a nice outlook over there. So this is all totally unshaded. It's going to do a fabulous job. And yeah, these all have the Tigo optimizers underneath. We've mapped them to the CCA, so we know exactly what each panel's doing, and we also have the rapid shutdown functionality. So if the AC is lost, because this building is remote to the house, the PV panels will shut down. So if any first responders are coming to deal with an issue here, or the customers wanting to isolate the panels to do some sort of maintenance, if they've got a leak in the roof or whatever else, that is very quickly and easily done. These are bonded as well. There's a lot of chat in industry at the minute about degradation of panels and also capacitive coupling. One of the best ways you can tackle that is through bonding your array frame and panels. Now, quite how robust they are to the fullness of time, these are out in the elements. So the bonding, you know, I don't have massive confidence that it's going to last the full 25 years of the array, to be completely honest. However, we've made a best effort to do something about it. In terms of the degradation, a lot of the solar panel manufacturers have dealt with that now. The panels come with technology built into them to try and counter against it. if you're ever encountering a serious issue of it, there are products you can get that can try and reverse the damage and stop it from happening. And I think it's a build-up of the way the neutral flows around the array. So you can actually take your negative, and bond that onto the array frame. However, you need permission to do that and special design considerations that, you know, I don't really want to get into on this kind of installation. But if you have got that on an array of yours, it's something you can think about. But like I say, with the panels of today, you know, it's more of an issue from 10 years ago than it is in the modern time of things. In terms of your capacitive coupling, laying out your strings in a sensible manner, keeping your cables clipped onto the rails with ties, making sure your MC4s are kept off the roof, that your string routing is trying to do the best you can to avoid any of that, and then again making sure your frames are bonded. If you have got any of that induced voltage and current into the array frame, again bonding it can take that away prior to someone touching it. Otherwise, the issue is when these get wet, typically somebody can come and make contact with the panel and feel a little tingle at best, and at worst have a nasty shock. The dangers are there on larger arrays. So it is something to keep in mind, especially when you're on a single story roof as we are here, and it's not beyond the realms of possible that someone might come along and touch the array itself. It is just what it is. It's the moisture will, over the fullness of time, find a way into the component. If you've got capacitive coupling and that's made it out onto the rails, wet people outside touching it, they will start to notice. These are split down into 2 strings just to stay. So we've got 6 panels on the left in a string and 6 panels on the right in a string. And the reason we did that is the cables come out in the middle, and it was just easier to divide the strings up, keeping those to sensible routing and lengths, as we've just discussed. So that's kind of the roof side of it. Pop some little clips in along the way showing how we mounted this system to the roof, but it's Valk mini rail. I've not got any up here to show you, but I will show you in other parts of the video if I've not already. They self-tap onto the steel sheets, and then just a case of clamping down as normal with the Valk mid clamps and end clamps. And like I say, once the guys have got the bird guard done, they'll pop some end caps on, just try and neaten up this as best we can. It is what it is in terms of where the array finishes in the, you know, the peaks and troughs of the roof. So you sometimes end up with a bit more rail stuck out one side to the other than you would like. But that's just the nature of the beast, and it's better that it's secured down for the fullness of time. But yeah, that'll look the business when it's done. So yeah, that's the roof. We'll go take a look at something else. So this is the workshop setup, and you can see we've got our Solux 6 kilowatt inverter. That's got its little earth bond on to the underside, and we've also got the AC rotary isolator. We've got a little power over Ethernet bringing some data down here just for the Tigo Connect and this Solux dongle. It's not something the customer's going to be monitoring, but we can get the warranties activated. It gives us some connectivity. Ideally, we would have brought direct LAN. Just wasn't possible down to here, but you can see we've got a nice stable connection and it's working very well. We've got our Proteus consumer unit here. This is going to all be labelled up, and you can see we've got our lightning sockets down here. We've also got the power brought through for the Solux inverter, and then we've got a little local socket over here running that, and the SPD. Absolutely brilliant products from Proteus, bidirectional, no brainer. We've got our IMO DC isolators. These are 16 amp varieties. As I say, 2 strings of 6 panels. 10 amps is the ISC roughly on the Trina panels. Pointing out with Trina's, they've got about 50 volts on your open short circuit voltage, so one to watch out for. I was going to try and do 1 string here because we used to jinkers, but it wouldn't work with the 12 Trinas just because of that peak voltage. You can see at the minute we've got about 1.4 kilowatts-ish, which is good. In here we've got our CCA, so the rapid shutdown, and we've also got our SPD. I'll show you a bit of that through the course of making the video if I haven't already. But essentially that is communicating with the tap on the roof, and if it sees an issue up there, this will tell it to shut the rest of the optimizers down. If this has a loss of AC, it will tell the optimizers to shut down, and it enables a safe state for anyone who's wanting to shut the system off. So AC rotary isolator here goes off, inverter goes off, tap shuts down, panel shut down to the optimizers, nothing comes through the strings. Same back at the house, if someone pulls the main service fuse, shuts the gateway down, all of it goes off. So that's that. We'll go and look at the all-in-one. So the all-in-one, as you can see, is down here outside. We're going to put a little canopy roof on. I will prove it and show you the footage of that. But I'm going to Alex tomorrow at Coventry, so I'm not going to be here. And we've run out of time today. So Matty and Nathan are going to pop that across. We've got a couple of outdoor sockets to pop on for the customer as well. But that will be up there tomorrow, and I will get some footage cut into the video. See, we've got our rotary AC isolator there with a steel wire armour coming in. That's to shut down the AIO. Existing cables for the customers, there's some Sky cables and all sorts going on, so I'm not fully sure what that is doing. But we've also got the EV charger just on the edge here as well. Nathan still needs to clean the lead up. Customer wanted there so they can pack the cars up here and charge up. So that is what it is. The gateway runs across this way, so we've gone underground just around this. As always, you've seen that loads on the channel before, so we've not bored you with the groundworks on this one. I'll take you and show you the gateway in a sec. But yeah, this is your 13.5 kilowatt storage. They've got about 15 kilowatt hours of power in there, but they declare 13.5, so you can expect to have that through the lifetime of the product. 6 kilowatts in and out, 7.2 kilowatt peak. It's an absolute powerhouse. It will keep you running off grid, and it will also keep your PV generating while you are off grid as well. And the M2 rotary isolators, if you're an installer out there, this isn't paid or sponsored, these are the absolute business. 63 amp variety just for the wiring room. You cannot go wrong with them. And again, when we're using them outdoors, no top entry, and make sure you're screwing through the nice fixing holes they provide you outside of the enclosure, so you're not penetrating any of the internals, allowing moisture to creep in. So they are absolutely fantastic. Let's go and have a look at the gateway. So this is where it got a bit tricky, because the customer already had an Octopus EV charge install that is doing a Zappy. Now these are all load limiting, and we've had permission to connect the second EV charger. However, it's in its own existing consumer unit, because these don't have double pole RCBOs, so we're not able to get that in there, unfortunately. Again, we've got the two consumer units, they're running out of these Henleys. Proteus, again, they were already existing, so I assume the Octopus engineers fitted those along with the main switch. Nothing too bad about that install, to be fair. Looked pretty decent. We've obviously been over the terminals and make sure they're nice and tight. We've then got our sub-main coming up for the inverter down in the workshop, and also over to the AIO and EV charger. And we've got our grid tails in, always grid tails coming in, load tails coming out to these Henleys, which do the Octopus EV point, and also the two consumer units over here. Now this could all do with being popped into one board, to be fair, but it's existing, it's all functional and working. It's not that old, so we're leaving as is for the time being. In here you can see we've got a 100 amp grid switch, so that's taking power from the grid up into the electronics of things. At the minute we're on bypass because we're still doing the commission, but then it will run through the load out to the consumer units and said EV charger. The EV charger for the GivEnergy system is through this Proteus bidirectional RCBO, and we then got our PV circuit and the AIO circuit, which again, type A RCDs, C32s, and they are up and running. The system is generating, battery is going. I'm going to go and see what the commission is at the minute, but I just thought I'd show you that. Sometimes these things are not a work of art just because of the layout, but it's perfectly safe and functional, and that will serve the customer for a very long time with nice, clean, renewable energy. So we're on a slightly less windy part of our walk, and I thought I would just drop into this video to talk a little bit about potential induced degradation. Now, we've shown either pre or post this clip how you can use test instruments to look for it and see if it is affecting your array. Sometimes the assumption can be that we've got faulty panels, faulty MC4 connectors, an issue with a DC isolator, cabling problem out on the array, and 99% of the time that will be exactly what you are looking for. But in some very small microscopic cases, you may have potential induced degradation. Certainly in older arrays, newer systems, a lot of the manufacturers have become aware of this and tried to engineer solutions into the panels themselves. Lots of clever technology in there now. But potential degradation is basically high potential difference between semiconductor material, so the cells and other parts of the module, your glass, your mount, your aluminium frames and such, and that potential difference creates current leakage. That's the migration of your negative and positive ions, and that can cause a negative impact on your array. Usually the negative ions, as I understand it, is flowing out of the aluminium frame, while the positive ions, so sodium, I think it's sodium ones, migrate to the cell surface, and these pollute the cell by reducing its photovoltaic effect. So that's kind of what it is. There's multiple approaches you can take in trying to stop it and spot it, and we'll get to that just now. So one of the biggest factors, I suppose, is the environmental area that a panel's installed. So if you're in a high humidity area, then obviously the presence of moisture in the air around the panels can cause this to be more of a factor in a very dry and arid area. So your system configuration also plays a part. So that's your layout of your array, and your panels that have got more negative, always the negative things of industry causing us trouble, isn't it? Can be the ones more susceptible to it. So yeah, they're the ones who are more at risk of suffering the effects of PID. And the chemical composition of the glass, so the encapsulating material, any anti-reflective coating, has been shown to have a big impact on the reduction of PID, and that's what I was talking about with panel evolution, where we've got our NMP type panels. It's all done in a way to try and mitigate a lot of the issues we'll see out installing this stuff and using it to the lowest possible denominator. And of course, basics like the resistance of moisture. So a lot of early panels, you know, the IP resistance, I guess, for want of a better phrase, maybe wasn't as good as it should be. But a lot of the more modern panels now, you know, they really are built more robustly, tested in much harsher environments before they bring them to market for sale. And as long as you are installing them in that condition, you know, you shouldn't have moisture ingress reaching the panels. That's one of the reasons they don't like them laid flat, because you can have moisture sit on the panel and then work its way into it. And that was one of the things I was concerned with my shed array, actually. And so far so good. Those Trina panels are holding up very well, and they do really only have like a 5-degree pitch at best. So they do hang a bit of moisture from time to time. And that was kind of a deliberate effort to see if I could induce a bit of PID into that array, if I'm being honest. But nothing as yet. So in terms of what you can do when you have detected it, 'cause it's all well and good doing your testing and coming to the conclusion that you have got a problem with that, but at that stage of the panels need replacing, is there things that you can do? And from what I've learned, it seems to be a case of it depends. So some of the PID damage can be reversible and some irreversible. So I think if you've got, what was it called? I can't remember now. I think it's electrochemical. So if it's been an electrochemical reaction, then that's irreversible. It's kind of damage and delamination within the panel itself, and you can't then, you know, reverse that. Now if it's the reversible type, you can get, I don't know if they're called anti-PID devices, or I'm making that up, but there's devices that you can put on your array, and my basic understanding is that over the nighttime period they do something in terms of putting ions into the array that reverses the effect and build-up caused during operation in the day, and that's something that needs to be installed in the string wiring. And a lot of the time, supposedly the period for them to regenerate isn't that large, so within a month or so you can see panels returning back to their optimal performance. If PID's been a factor for a long time, so if it's a really old array and it's only just kind of been looked at and discovered, you know, that period can be increased to months, potentially years, and then you've got the decision as to if that's worth it or if it's better to just replace the array. You know, I guess that's a financial decision based on the size, cost and scope of doing that work, and also the environmental impact as well. So the best way of avoiding it, if you're still planning your array, is to use cells that are resistant to it. Now there's different levels of that, so lots of modern cells have, you know, that built in standard anyway. Now it's much less of a factor, which is why you don't hear a great deal about it, to be honest. It's a very niche, microscopic subject of industry. However, you know, finding it and preventing it at the origin of an install is way better than discovering it years later, and the potential contractual impacts that might have upon you from an array that's been underperforming due to it. You know, when your efficiency tests can very easily detect it. But yeah, select your panels correctly. If you're in an area which does suffer from high humidity, which is not especially common in the UK, where we've got those high temperature, high humid environments. You know, thinking more of these tropical parts of the world than little old Britain. But yeah, selecting the right panel to be resistant to it. You can also look at bonding of your array frames and panels, and that's not necessarily to earth either. There's some research that shows bonding to the negative string can bring a reduction in the potential occurrence of PID. Now there is other legislative and regulatory requirements to satisfy if you're going to go down that road, and in most domestic small array systems, you know, it's going to be of negligible effect. I would just say consider bonding your array frames to earth and ensuring your panels are purchased from a reputable supplier and a well-known, well-established manufacturer that's got a good history of producing these components. And then as long as you've taken those steps to install in the right way, your warranty will be intact. So yourself and your customers can be safe in the knowledge that if this does become a problem, you've got avenues to go down to get those panels replaced and the problem resolved. It's not something we've come across as yet. We do check for it on every single project with our test instruments, and I would advise all other solar installers out there to look beyond just the safety tests, especially on arrays with optimizers, when it's quite hard to do that anyway, and make sure your test instruments can do your efficiency tests and you can get a clear sight within the first week or two of operation how your array is actually functioning. Back to site. And there we have it. That's the system on the roof and generating the whole job finished. This has been a challenging one because the components are spread around quite far and wide on this install, as you will have seen. We've tried to come up with the best solution to get value for the customer, but also making sure we're covering off the safety aspect of things as well. Just to say, as always, if you are a consumer looking to get a solar PV or battery storage system, please do get in touch with us. There's in the description a link over to our website, and you can drop an email across. It'd be an absolute pleasure to propose something for you. If you're a manufacturer and you'd like to work with us and showcase your products out in the real world, installed by qualified and competent electricians, where we can explain to other people of industry how these things work and also some of the pros and cons to consumers, then please do get in touch as well. If you've got any questions around this install, drop them in below. I always watch out for the comments. I love getting involved in some of the chat there. Any tips or tricks to help us improve and be better at what we're doing are all gratefully received, and otherwise we will see you on the next one.